Hi, good afternoon. Instead is already unlocked. Please sign your attendance now. Okay, let's continue our lesson. So I'm going to share the screen. All right, can you see my PowerPoint?
Yes, sir.
Okay, thank you. All right, let's continue to this electric potential. Okay, this is important. Potential difference, you always see potential difference when you study physics, especially in this electricity. Okay, but actually potential difference or electric potential basically is come from electric field. Okay, it's because we know that electric field basically is the region for the charges to have interaction. Okay, so therefore when we say interaction basically involve the forces, so it's either attraction or repulsion. Okay, and because of that there will be some movement occur between the charged particle, therefore it involves energy. All right, so therefore from the previous lesson we already seen this electrostatic force, okay, electric field itself, and also the work done, or so-called the energy involved, right, when we have the interaction. Okay, so today we will come to this item called electric potential. So this is also related to energy. Okay, so potential difference is defined as the changes. Okay, when we apply these terms here, difference, right? Potential difference means that is the changes of potential energy per unit charge between 2 points. Okay, so you look at that. Potential is related to energy actually. Okay, and you learned mechanics before during your high school. Okay, so I already give the example for this gravitational potential energy and the kinetic energy, isn't it, in the previous lesson, right? So if you raise an object to a certain height above the ground, actually you're giving the potential energy to the object. All right, so when you let go, the object will fall, right? It's because the gravitational potential energy will be converted to kinetic energy. All right, and we know that why the ball is dropped, okay, is because, or why the object is dropped, is because of the gravity. Means that there is a force, okay, try to pull the object downwards. Okay, so when we have this electric potential, okay, so
sorry, sir.
Yes.
Should we record this session?
Oh yeah, damn it. Okay, one moment, yeah. Let me okay, one moment. Let me unshare first. Okay, recording started. Okay, I'm going to share the screen again. Okay, can you see my screen? Okay.
Yes, sir.
Yep. Okay, sorry about that. Okay. All right. Okay, this is where we stop. Okay. All right. So therefore, okay, when we come to this potential energy in electric field, this is basically similar to the potential energy when you go to this gravitational field, right? It's the same, right? So when we raise the object, actually we're giving the potential energy, right? So therefore, in this case, if we try to move the charges around, okay, so these charges basically will depends on the electric field being set up, okay, right? Okay, it's just like our Earth is a big charge, right? And the object is a small charge. Can you imagine that, right? So our Earth is a big charge, so our Earth is set up the field. All right. So if you try to move the small charge or you try to move the small object, okay, it will strongly depends on the field set up by Earth, isn't it? Understand the situation or not? Right. So no matter how hard we try to throw this object upward, but in the end the object will still go back to the ground, right? It's because, right, the Earth actually having a stronger field. Okay. So same thing here. When you set up the electric field and we try to move the charges around within the electric field, it will involve the energy. Okay, right? Okay, let's see what happened here. Okay, you have seen this in the previous lesson. The work done in moving a charge from the negative plate to the positive plate will be given by this formula, right? W equals to QV. Okay, so and from there actually we derive our formula of the electric field, isn't it? So E equals to what I call the V over D. Okay, right. So therefore from here, all right, so we can also equalize this W equals to QV to FD, right? Do you see that? Okay, and the F here actually related to the electric field. Okay, so therefore I can try to do a little bit of modification here. So let's take a look. QV equals to FD, right? And we know that, oh, sorry, this is the electrostatic force, okay? So, and this is actually equals to QE. Do you see that? All right, okay. So therefore, if this side I maintain it as W, okay, so you will get W equals to QED. Okay, right? Am I right? Okay, so the E here, okay, we can change it V over D, right? So therefore, this is how we get W equals to QV, and if we rearrange it, you will see that potential is given by W over Q. Am I right? Okay, so therefore this is suit to our definition here. Okay, look at that. Electric potential energy per unit charge. Do you see that? Okay, so therefore this V actually is energy per charge. Okay, understand what is going on or not? Right. So therefore, okay, we try to link the energy to the field. Okay, and we know the field is set up by the voltage or the potential over D. So therefore, we try to use this relationship, okay, to get this equation. So in the future, okay, you can either write W equals to QV or V equals to W over Q. Okay, so the W here is the work done. The V here is the electric potential. Okay, so you don't need to derive this actually. Okay, you just try the question for several times and you can eventually remember this equation. Okay. All right, so this is how we get this. Okay, this is important. So electric potential, sometimes we call it as a voltage, right? So therefore the unit for this electric potential, okay, to be exact, is the SI unit, is volt, right? Okay, you learned this before in the high school, isn't it? Okay, more importantly, okay, this is very important because some of you already attempted the question, okay, and you face some problem, okay, like early this morning, someone re-text me on that, okay? So you have to be careful with that. Look at that. Electric potential is a scalar quantity. Okay, be careful, okay? Electric potential is a scalar quantity. So what does it mean by scalar quantity? Scalar quantity means that it will have only the magnitude. There's no direction or there's no specific direction. Okay, so basically you can try to observe from this equation. Okay, look at that. V equals to W over Q. Okay, W is energy. We all know that energy is a scalar quantity, isn't it? Since high school, you already learned that energy is a scalar quantity. Okay, charge is also a scalar quantity. Okay, so scalar divided by scalar, definitely the V here, also called the electric potential, is also scalar quantity. Okay, so therefore the way we handle the problems or question of this electric potential, okay, we have to do it in a scalar way. It's unlike what we had for this electrostatic force. Still remember, I show you the vector method to solve the electrostatic force problems and also electric field problems. Okay, so since electric field and what I call the electrostatic force both are vector quantity, so means that magnitude and direction both are equally important. All right, so we have no choice. We have to use the troublesome way to get the solution. But right now, okay, it's clearly you can see from this equation, electric potential is a scalar quantity. So it's such a big relief actually. Okay, so as long as you don't need to use the vector way to solve it, okay, so I think the way we handle electric potential will be a lot easy. Okay, will be a lot easier compared to those vector problems. Okay, so it means that you don't need to take care of the direction. All right. Okay. For radial field, okay, so there will be a point of zero electric potential. Okay, so it's always defined as a point at infinity. Okay, right? So it means that it's a point that very far away. Okay, so this, I mean, from the point that we set up the electric field, okay, if you go to a very, very far distance from the point we set up the electric field, so this will be the infinity. Okay, and this infinity point basically will give us zero electric potential. Okay, right, therefore the electric potential at a point in an electric field is defined as the work done in moving unit charge from infinity to the point. Okay, this is very important. Later I will further explain this statement. Okay, so this statement actually comes from the formula that I show you just now. Okay, let me write it down for you. Right, so this is actually come from this. V equals to W over Q. Okay, V equals to W over Q. All right. Okay, so if you combine the equation 1.7 and also the equation 1.10, okay, and we assume D is equals to R, so we can also write electric potential as 1 over 4 pi epsilon naught Q over R. Okay, right, so far you already learned three important equations for this electric field. Okay, let me write it down here for you to compare. Okay, so the V here is electric potential, and we learn force, right? The electrostatic force. So it is equals to 1 over 4 pi epsilon naught. Okay, so Q1, Q2 over R squared. And electric field will be 1 over 4 pi epsilon naught Q1 over R squared. Okay, so and this what I call the electric potential will be given by V equals to 1 over 4 pi epsilon Q over R. So in this case, you can place this as a Q1, right? Okay, so still remember the meaning of this equation. E equals to 1 over 4 pi epsilon naught Q1 over R2, right? Still remember the meaning of this. Okay, so the meaning of this basically is the electric field due to who? Due to Q1. All right. So therefore, this equation here for the electric potential, we will say that this is the electric potential due to who? Due to Q1. Right? Understand the situation? Okay. So I hope you don't mix up these three equations, right? Because it's quite common. It's quite common in the exam. Student apply the wrong formula. Okay, so you must recognize F is the force, E is the electric field, okay, and V is the electric potential. Okay, so the meaning of this equation, right? Because look at that, we have the Q1 here up there, right? So therefore, this is the electric field due to Q1. Okay, and this equation for the electric potential. Okay, so this equation will tell you that this is the electric potential due to Q1. Okay, and if you want to be more precise, Okay, if you want to be more precise, okay, I will add electric field due to Q1 at distance R. You see that? Okay, that will be more precise. Okay, and for the formula 1.11, the electric potential, I will say this is the electric potential due to Q1 at distance R. Okay, that will be more precise. Okay, so I hope you understand what is going on here. Okay, let's carry on. Okay, now I'm going to give you the important concept of this electric potential. Okay, so imagine we have a charge Q1 here. All right, so this charge Q1 set up the electric field. Do you see that? Okay, so therefore the whole yellowish region here, okay, I will say this is the region of electric field. Okay, so this is the region of electric field. Okay, so this is so-called a territory marked by this Q1. Okay, so what if I have another charge? Okay, in this case, we are saying that Q2 is a test charge, right? Q2 is a test charge. Okay, so this is the test charge. So remember the same idea when I explained electric field to you. Okay, someone set up the field. Then, of course, we need somebody to test or to experience the field, isn't it? Right, of course, the best candidate here, if this is an electric field, the best candidate will be the charge particle, isn't it? So in this case, again, we call our friend here, okay, a test charge to examine the electric field set up by Q1. Okay, and of course, at first we put this Q2 at the infinity, okay, position, which means it's very, very far away, okay, from Q1. Okay, now the problem is, let's say the Q2 is also a positive charge, let's say, okay, this Q2 is also a positive charge. And if you want to bring this positive charge, okay, come near to this Q1, okay, we learned the nature of charges before, isn't it? Right? Positive charge and positive charge, what happened? They will repel each other. They will try to push each other away, isn't it? All right. So therefore, if you need to bring this positive charge come near to this Q1, you need to do work, right? Or you need to supply energy to Q2, isn't it? In order to bring this Q2 near to this Q1, isn't it? Okay, let's say I try to bring this test charge Q2 to this location. Okay, you can see the dotted line here, isn't it? So this is actually the circumference setup, okay, for the radius R. Do you see that? Okay, so if you want to bring this test charge come to this location, okay, which is at a distance R from Q1, okay, so what happened? Okay, so in this case, you want to bring Q2 come to this position. Of course, this Q2 definitely will feel a very strong repulsion from Q1, isn't it? Maybe at far, the repulsion is not that strong, but when it getting closer and closer to Q1, the repulsion will be getting stronger and stronger. Am I right? Okay, so therefore, if you want to bring this test charge come near to this Q1, you need to do work. Okay, and what kind of work you need to do? Okay, at first, you have to recognize that this dotted line, okay, will give you the potential, right? It will give you the potential of V equals to 1 over 4 pi epsilon naught Q1 over R. Okay, so this dotted line basically will tell you that this is the potential, okay, set up by this charge at this distance. Okay, so therefore, if you want to bring Q2 come to this location at distance R from Q1, you need to do work. Okay, so what will be the work? The work will be W equals to Q2V. Okay, W equals to Q2V, and maybe you can't see what is going on here. If you rearrange this equation, you get V equals to W over Q2. Okay, and if you go to the definition of this, it will be the energy required to bring Q2 to the distance R from Q1. Do you see that? Okay, understand the idea or not? Okay, this situation basically is just like when we try to lift up the ball from the ground. We try to lift up the ball from the ground, okay, and we try to means that we try to against the gravity. You see that we try to against the gravity. If we need to against the gravity, we need to do the work on this ball, isn't it? Okay, so same thing here. If you want to bring this charge come near to Q1, right? Basically, you need to do work, or you need to supply energy to Q2. Okay, so therefore at this location, okay, you need this much of energy to bring Q2. Okay, understand the situation or not? All right, so let me change the situation a little bit here. Okay, what if okay, what if I have another charge? Okay, I have another charge. Okay, let me clear. Okay, it's kind of messy here. Okay, let me clear everything. Okay, so what if I have two charges here? Okay, I have another charge here. This is Q3. Okay, this is Q3. Okay, so together with Q1. Okay, again, this is also positive, let's say. Okay, so when it comes to this situation, if I want to bring this charge Q1, okay, sorry, Q2, to this location, distance R1 from Q1, and then distance R3 from Q3. So what will be the work done? Okay, and you understand the situation, no? Okay, just now we have only one, what I call charge to set up the field, isn't it? Just now when I explained this to you, okay, the Q1 is the only one who set up the field. Now I have another fella, okay, Q3. This is also a charge that, okay, set up the electric field as well. Okay, understand the situation? Okay, so therefore I have two charges set up the electric field here, and now I want to bring the test charge Q2 to this specific location here. And this specific location is at the distance of R1 from Q1 and at the distance of R3 from Q3. Okay, so what will be the work done? Okay, so that will be very simple. First thing to do, you have to get total potential at, okay, let's say this is the point M, okay, at point M. Okay, this is the first thing you shall do, okay, to get the total potential at point M. Okay, the reason is because you having two charges to set the field, so therefore you will have two electric potential at this specific point, isn't it? Okay, so therefore the total potential now will be given by the potential given by charge number 1, which is the Q1, and the potential given by the charge Q2. Do you see that? Right. So therefore at this point M, we will have this potential. Okay, right. So therefore, right, this will be definitely equals to okay, I use a short form, Q1 R1 plus K Q2 over R2. Okay, right. So still remember just now we said electric potential is the scalar quantity. So therefore, look at that. The way I do it is basically just the scalar addition. Do you see that? This is a scalar addition. Right, which means we don't need to bother what is the direction, okay, right? We don't need to bother what is the direction and so on. What we need to know is purely just the scalar quantity. So therefore, you can just add directly, okay? Understand? Right? So get back to our question just now. Okay, we already know this is what I call the total potential. And how about the work done here? Okay, how about the work done here? Okay, I label it as number 2. Okay, so therefore the work done, okay, get back to the definition, right? the work done basically is the QV. You see that? QV. Okay, and the Q here, right, it will be the Q of the test charge. So this is Q2, right? So therefore, if you rearrange everything, so now V will be W over Q2. Okay, V will be equals to W over Q2. Okay, or in other words, if you extend from here, it will be Q2. Okay, here will be Q1 plus Q2, which is this. Okay, understand the idea or not? All right. So therefore, if you have two charges set out the field, you want to bring the charged particle to this specific location M. This is the work done, right? It will be given as Q2 times with V1 plus V2. Okay. All right. Understand the situation or not? So whenever you apply, yes.
Sure. Why are we only considering the charge of Q2 and not also Q3?
No, the Q3 and Q1 both contribute the field. Do you see that? That's why I mentioned just now. Okay, Q1 and Q3 set up the whole field. And we want to bring Q2 into this region. So how much energy we need to do on that? Or how much energy we need to supply to Q2? Got it? So therefore, here the substitution is Q2, because from the definition of V equals to W over Q2, okay, if you want to overcome this potential, you need to do this much of work, or you need to supply this much of energy to who? To Q2. Understand? Right? Because Q2 is the object that we are trying to move. Understand or not? Okay?
Yes, sir. Yeah.
Okay, I repeat one more time here. Just I'm quickly repeat it. First, you must know who set up the electric field. Okay, whenever you have this type of question, you must know who set up the electric field. If I have two charges here, right, which is Q1 and Q2, so Q1 and Q2 will be the charges set up the electric field. Okay, right, and who is going to experience the electric field set up by these two charges? Q2. You see that? Okay, Q2 is the one to experience the field set up by these two. So if I bring Q2 near to both of them, right? So what kind of energy you need to supply to Q2? So it will be given by W equals to Q2 times with V, right? And of course, the V here is the total potential given by Q1 and Q3. Okay, understand the idea or not? Clear?
Yes, sir.
Everyone clear on this point?
Sir.
Yes.
If we make the Q3 as the object, so so the electric field will be between Q1 and Q2.
Okay, good question here. All right, let me erase everything. Okay, your friend suggested a very good situation here. Okay, so now Q2, okay, maybe I should go to a previous page because, okay, here. All right, let's look at this situation. Okay, good suggestion actually. Okay, look at that. Now we have Q1, we have Q2 here. Okay, and just now the Q3 is here, right? So this is your Q3, the positive charge. Okay, now we try to bring Q3 to this point. Okay, let's say M. Okay, so when come to this situation, okay, this is important for us to know what is the distance between Q1 to M, which is R1, and what is the distance between Q2 to point M, this is R2. Okay, now different story already. Now Q3 is the object. Okay, Q3 is the object. We want to bring Q3 to point M. Okay, so first of all, you have to answer this question. Now, who set up the electric field? Okay, first question. Okay, who set up the field? Okay, if you want to, now Q3 is the object. You want to bring Q3 to M. Now, who set up the field? Very straightforward, isn't it? Now, Q1 and Q2 set up the field. Am I right? Okay, am I right? So therefore, at this point M, Okay, this is number 2. At point M, total potential V will be given by what? It will be V1 plus V2. Am I right? Okay, so V1 will be K Q1 R1. I think I made a mistake just now. I should write. Okay, never mind. Let me complete this. Then I try to return to just now that one. So this is K Q2 over R2. Okay, so this is the total portion potential. Okay, this is by Q1 and Q2. Okay, right. Okay, now I go back to just now to correct my mistake just now. Okay, understand that now? Just this situation is Q1 and Q2 set up the field, and Q3 is the object. Okay, let's get back to this one. Okay, so now the other situation is that this is the previous one. Okay, now this is Q3, and now we bring Q2 to this location M. Okay, and of course your Q2 now is the object. Okay, this is the object. Okay, so this is the distance R1, and this is the distance R3. Okay, so first question, who set up the field? Okay, first question, who set up the field? Okay, now is Q1 and Q3. Okay, look at that. Just now we are using Q2 to set the field, isn't it? So therefore, just now is Q1 and Q2 set the field, but now we change the object. Now Q2 is the object. All right. Okay, so now who set the field? It will be Q1 and Q3. Okay, so therefore, what is the total potential? I think I just now make a mistake. Yeah, I think I made a mistake. This should be V1 plus V3. My mistake just now is you just change the 2 to 3. Okay, so therefore this will be K Q1 over R1 plus K Q3. Okay, because now Q3 is the one also the one who set the field R3. Okay, understand? Clear? Yes, class?
Mr. Lim?
Yes.
Does the sign of the charge make any difference?
Later, that one. Okay, one by one. Okay, I will answer that question. Don't worry. Okay, but so far, any question on that about the concept of this electric potential? Any concept? Any question on the concept?
Sure. When we're looking at the question, we're determining the field set up by the two electric charges based on their position, or it's going to be given in the question?
The question will tell you who set up the field.
Okay, thank you, sir.
The question will tell you. Don't worry. Okay, it's just like the previous example that will tell you the target. Remember, I always remind you all whenever you handle this question, first thing to do is identify the what they call the target, right? So the question will tell you where will be the target. Okay, later there will be one tutorial question. Okay, it's a very good question, which is question number 16. Okay, I will show it to you. Okay, right, but so far, any question? Any question? Okay, so therefore, yeah, any question? No question, yeah? Okay, so therefore in the future, okay, whenever you have electric potential question, okay, you must know how many charges set up the field. Okay, if you have 3 charges set up the field, means that you're going to have 3 potential. Okay, and you have to add all the 3 potential together to get the total potential. Add directly. Okay, you have to add directly. Okay, so just now someone asked, how about the sign of the charge, right? Okay, it's a good question here. Right, so I will jump straight to this. Okay, let me unshare this first. I will jump straight to one of the tutorial question, which is the question number 16. Okay, this is the one. Okay, right, so damn it, same problem again. I cannot just show which switch. I have to unshare first. Sorry about that. Okay, let me unshare first and then I share again. Okay, so can you see my PowerPoint now? Right, so this is the tutorial question which involves the electric potential. So, okay, let's take a look on that. Okay, are you ready? Okay, let's look at this question 16 here. 3 charges are placed at 3 corners of a square. Okay, find the electric potential at point A. Okay. So the first sentence here, 3 charges are placed at 3 corners of the square. So this actually gives you the information who set up the field. You see that? He will give you the information who set up the field. And the second question, find the electric potential at point A. So this is actually your target. Okay, so this question is just similar to those electric field question, right? So remember in one of the lesson I did explain that, okay, if you need to find the electric field at one point, okay, so the question could be either you need to involve a test charge or you may not involve a test charge, right? Still remember that? So for this question number 16, okay, at the target, which is the point A here, right? So this example, actually, we don't need to involve a test charge. Okay, of course, I can always switch this question, right? I can always switch this question to the other situation. But this question, very obvious that it doesn't involve test charge. It just purely to look for the electric potential at point A. And the point A will be the target. Okay, so how are we going to handle this? Right, remember just now I said, you have to know who set up the field. So it's very obvious, 3 charges. You have 3 charges that set up the electric field. Okay, and where will be a target? Target will be the point A here. Okay, so remember, if you have 3 charges to set up the field, there will be 3 electric potential, right? Okay, so as a result, okay, you have to do a little bit of mathematics first because we need to know what is the distance, right? From Q1 and Q3, the distance is very obvious because this is a square, right? It will be 20 centimeter, 20 centimeter. But for Q2, you need to find the diagonal length here, right? Which can be obtained directly from the Pythagoras theorem. Do you see that? Right? It's a square root 20 square plus with 20 square. You get 28.3. So you need to get this distance first. Okay. So it's just like what I mentioned just now. You have 3 charges set up the field, so therefore you have 3 potential here. If you look at this part carefully, okay, so this is actually your V1, this is actually your V2, and this is actually your V3. Okay, so you have 3 charges set up the electric field, therefore you have 3 electric potential. Okay, and since they are scalar quantity, look at that, we just add them up directly. Okay, we add them up directly. But, okay, I'm going to answer the question from one of you just now. How about if the charges is having a negative sign? Look at that. You have 3 charges here. Okay, so Q1 is positive, Q2 is negative, and Q3 is positive. Okay, so what shall we do with the negative charge? Okay, the answer is that, okay, if the charge carry a negative sign, you have to include the negative sign in your calculation. Okay, understand? Clear? Everyone? Clear? Any question?
Sir?
Yes?
Is it for scalar calculation we include the sign?
Yes, I already mentioned many times just now. Okay, vector quantity, when the calculation involves vector, okay, we need to make use of positive and negative charge to construct the vector diagram, isn't it? Okay, so therefore in the calculation there, after we construct the vector diagram, in the calculation there, you don't need to include the sign of the charge anymore. Because if you include, okay, you're going to mess up everything. Okay, the reason is because we already make use of the sign of the charge to construct the vector diagram. Okay, but electric potential is a scalar. Okay, so it's different situation. Okay, so electric potential is a scalar quantity, so therefore okay, if you need to get the total quantity for a scalar quantity, okay, what you need to do is just direct addition. Okay, direct addition. So as a result, because this is the direct addition, so therefore the sign of the charge will be very important. You have to include the sign of the charge. Okay, understand? Clear, everyone? Clear or not? Hello?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
I just want to enhance or to strengthen your concept. I will go straight to another example. Okay, let me jump to the last one. Okay, this one. This is the question from one of the past exam question. Okay, it's 2012 and 2013 academic year. Okay, let's take a look at this question. Wow, it's so scary, right? So many charges there, but nothing to worry. Okay, nothing to worry. If you look at the question carefully, determine the electric potential at point A. Okay, determine the electric potential at point A. Okay, so first of all, they will already tell you this is the target. Okay, this is the target. And they never tell you, okay, who set up the field, but it doesn't matter. Okay, you can always refer to this figure Q1. Excuse me. Okay, excuse me. You can always refer to the figure Q1. Okay, point A is somewhere or at certain distance from all these charges, isn't it? You have 1, 2, 3, 4, 5. You have 5 charges there. Okay, you have 5 charges there. Okay, so therefore these 5 charges set up the field. Okay, these 5 charges set up the field. Okay, and what you need to do is you need to get the electric potential at this target point or point A. Okay, right, so still remember what I mentioned just now. If you have 5 charges set up the field, so how many potential there? There will be 5 potential. Do you see that? Okay, so as a result, okay, look at that. There will be 5 potential. Okay, so this is V1, this is V2, this is V3, this is V4, and this is V5. Do you see that? Right, 5 charges, 5 potential. Okay, and electric potential is a scalar quantity. So what you need to do is direct addition. You don't need to bother, you don't need to care about the direction. Okay, and of course, if this is a scalar quantity, therefore the sign of the charge will be very important. So look at that. Okay, this is the negative charge. Do you see that? Negative 8 nanocoulomb. Okay, and this is also the negative charge, negative 16 nanocoulomb. Okay, you have to include the sign of the charge in your calculation, and in the end you get 1580.5 volt. Okay, which is the electric potential at point A due to the 5 charges given here. Okay, understand? Clear?
So I have a question.
Yep.
Okay. Now that we know that electric potential at point A is 1580.5 volts,
Yep.
Does this mean that how do you say, the energy needed to push the test charge from A to any of these charges?
No.
Yeah.
Okay. Let me help you to rephrase the question. Okay. Right. Let me help you. Okay. Okay. This is what I want to add into this question as well. This is what I add into this question as well. Okay. But it's great you asked that. Okay. We already find the electric potential at point A is 1580.5 volt, isn't it? Okay. What if there is a second question here? Okay. What is the energy, okay, to bring a test charge of 1 nanocoulomb from infinity to point A? Okay, understand the question, huh? What is the energy to bring a test charge of 1 nanocoulomb from infinity to point A? Means that we will have a test charge somewhere here. Okay, this is 1, okay, positive 1 nanocoulomb. Okay, and the location is infinite. Okay, we want to bring this charge to this location. So therefore, what will be the work done? Okay, right? Understand the situation or not? Okay, so therefore this will be very straightforward. Okay, so remember what I showed you just now? It will be W equals to, okay, let's say test charge, we label it as Q test. Okay, Q test. So therefore the work done will be Q test, okay, times with VA. Understand? Okay, got it?
Yes.
Understand? Can I?
Yeah.
Did I answer your question?
Actually, my question was something else. What about the energy needed to push a charge from A to any of these charges that set up the field?
If that's the situation, all right, then different way to play it already. Okay, so let's say, okay, that will be, you don't need to look for VA already if that's the case. If your question is you have a test charge here, okay, at this point A, you want to bring, let's say, bring it to the location of this 5 nanocoulomb. Okay, let's say that, right? So therefore, in this situation, how many charges have a field? You have only 5 charges cell a field, isn't it? Because you bring the test charge to the location of 5 nanocoulomb charge. So therefore, the field set up by this fella can't be counted already, isn't it? Right? So in this case, there will be it will be 4 charges set up the field. Understand the situation or not? Okay, because now you try to move your target to this point. This is the target now. I mean, according to your question, the 5 nanocoulomb charge will be the target. I mean, the location, to be exact, the location of this 5 nanocoulomb charge will be the target of the question. Understand? Clear or not?
Yes.
Got it?
Yes.
So if you change the target of the question, means that the charges who set up the field will be different as well. Understand the situation or not? So now, if you say 5 nanocoulomb location will be the target, this fella, the -8, +10, +15, -16. Okay, these 4 charges will be the one who set up the field. Okay, and we always, we never bring the test charge as part of the electric field being set up. Understand? Okay, we always ignore the test charge. Right, we assume the test charge will never contribute to the electric field. Okay, so therefore the question whether the target, right, the point of the target is a point or is a charge, it doesn't matter, right? You will get the same potential. Okay, clear?
All right.
Okay, clear? Sure?
Yes.
Any I mean, how about others? Clear or not? Others? Any question?
You processing.
I'm clear, sir.
Wait,
Okay,
sir,
all right,
can,
good.
can you explain again why 5 nanocoulomb is not counted?
Okay, let me clear all this thing again because it's messy. Okay, look at the formula here. Okay, if 5 nanocoulomb is the target, okay, let me get the pointer. Okay, if the 5 nanocoulomb is the target, you look at the equation of electric potential. Okay, the electric potential formula is always the, I mean, down there, the distance basically will be the distance from the charge to the target, isn't it? You look at the way we write it here. Okay, we are actually, okay, look at the R1. Okay, this R1 actually is this distance. Do you see that? Okay, let me get back to the pen. This distance is, oh my, okay, this distance is R1, this distance is R2, this distance is R3, and this distance, okay, one more here. This distance is R4, this distance is R5. Do you see that? This is when we take A as a target. Okay, but what if now we take this 5 nanocoulomb as a target. Okay, now look at that. Now, if this is the target, if, okay, I put here, if this is the target, so the distance, right, it will be different already, isn't it? The way we consider, because this is the target, so therefore we need to take the distance from the charge to the target. So this is R1, this is R2, this is R3, and this will be R4, right? Okay, so how about the 5 nanocoulomb charge itself? What is the distance from the target? Yeah, just now who asked me this question? Why the 5 nanocoulomb cannot be taken into the consideration? Now, can you tell me what is the distance from the from the 5 nanocoulomb to the target?
2.
Huh?
I mean, wait. The distance from the sorry.
location of the 5 nanocoulomb is the target already now.
Oh.
So what is the distance from the target to the 5 nanocoulomb charge?
0.
Anyone can help?
Is it 0, sir?
Sorry again?
Is it 0?
Yes. Right? Because you set the 5 nanocoulomb as a target, right? So what is the distance from this 5 nanocoulomb to the target? So the distance will be 0, isn't it? Am I right?
I see. I understand, sir.
Okay, so therefore, if you look at the formula for potential, V equals to KQ over R. If the distance is 0, can you still count? You cannot count this charge already, isn't it? Because it doesn't give you any, it won't give you any meaning at all, isn't it? Right? Agree?
Yes.
So everyone understand what is going on? Okay.
So I have a question.
Yes.
For the K, right, isn't it supposed to be 9 times 10 to the power
I
9?
already mentioned many times. Okay, you can straight away use 9 times 10 power of 9, or you can straight away use this 4 pi epsilon 0, which is 1 over 4 pi times with 8.5 times 10 power minus 12. It doesn't matter, right? Both will give you a very close answer. Okay.
No,
So,
why is there a 1 times 10 to the power negative 9?
again?
Why is there 1 times 10 to the power negative 9?
Nano.
Oh, okay.
Okay.
Thank you, sir.
All right. Okay. Any other question? Yes. Any other question?
Question.
Yes. Go ahead.
So that means that if in the system all the charges are negative charge, so we're going to get a negative potential, and that means the energy is also going to be negative, right?
Yes. But okay, for scalar question, it's very straightforward. What you see, what you get. Got it?
Yeah. So what does it mean by negative work done?
Okay. You see, the situation. Okay, I just that's the reason why I proposed the extra class. You see, because you will have a lot of questions, but seems like no one responds to that. Okay. Only 70 student response to my request, so I'm not sure whether I should have the extra class on this coming Saturday or not. Okay, all right. Okay, get back to your question. Look at that. So all the while we are talking about what they call, we try to bring a positive test charge to the location of what they call the positive charge, isn't it? What if we change the situation? Okay, this is our Q1, and our test charge is negative, right? Our test charge is negative. I want to bring the negative charge come to this location, right? So first of all, can you tell me this is attraction or repulsion? Yes, the one who asked the question just now, can you tell me this is attraction or repulsion?
Attraction.
Attraction. So if attraction, do we need to do work to bring this charge to the location of this? Let's say we have a point M here. This is the target. Do we need to do work to bring this negative charge to point M, or it will go automatically?
It will go automatically.
Yes, exactly, right? It will go automatically, isn't it? Right? So therefore, in this case, we don't need to do work, but he will go automatically to this point M. So in other words, who is doing the work actually? Definitely it's not me, it's not you, it's not the external agent, but who going to do the work? Who attract? Okay, if you want to know who do the work, you have to answer this question. Who attract this Q2? Yes, anyone can answer this question?
It's the electric field.
Yes, it's the electric field set up by Q1. Do you see that? Right? So it's the electric field set up by Q1 to attract this Q2 to point M. As an external agent, right? We don't need to do any work, isn't it? Right? If we place a charge there, it will automatically go to the target point, point M. Okay. So therefore, in this case, you look at the work done. W equals to Q2 V1. Am I right? Okay, because V1 is the electric potential set up by Q1. Am I right? So if you put all the substitution into your answer, you will get a negative answer, isn't it? Am I right? Hello?
Yeah, yeah.
Okay, so what does it mean? Okay, in the world of energy or in the world of work done, okay, if the work done carry negative sign, okay, means someone, okay, do the work, and this work actually cause a deficit for the one who generate the energy. In this case, electric field do the work. It's just like, okay, when you come to the business world, you are either having the profit or you're having the loss, isn't it? Right? So since this time, we are not the one who do the work, but it's the electric field to do the work. So if you stand at the position of electric field will be the one who lose the money. Do you see that? In this case, we'll say he's actually contributing the energy, right? So it's considered as expenses for this Q1. Agree or not? Hello?
Yeah.
Okay, so therefore it carry a negative sign. Okay, but you don't need to bother much about the sign because this is a scalar quantity. So what you see, what you get. Just that the meaning of the negative here is depends on who is spending the energy. Okay, who is spending the energy, right? So because all this question is centered at the electric field. Okay, so therefore, if the electric field earn the energy, then he will have a positive sign. If the electric field lost the energy, it will have the negative sign. Understand it or not? So in this case, the electric field attract the point charge. So he need to do work, isn't it? So therefore, from the point of view of the electric field, okay, is considered as a loss, isn't it? Right? Okay, but as an external agent, if we need to bring the charge, let's say, go back to just now, this is a positive charge. We want to bring the positive charge to the location M. Actually, there will be a repulsion, isn't it? And in that case, electric field, definitely he won't do a work, isn't it? Because he don't want this is positive charge, he will repel it. Do you see that? So we are the one bring in the charge, we need to do work, right? So therefore, from the point of view of the electric field, okay, he don't need to do anything, but he earned the energy. Do you see that? So therefore, the calculation there, you will see a positive sign. Understand?
Yeah.
How about others? Do you know what the hell is going on?
Yeah.
Sure, ah?
Yeah. Yes.
Yep. Clear or not?
Horizon.
You sure, ah? You say all right, but later
I know.
exam not all right, then GG, ah. Okay.
Sir,
Yes.
what about two negative charges?
Then there will be repulsion, you see. Two negative charge, look at that. Two negative charge. Okay, the Q2 itself is negative, right? And when you count the electric field from the first charge, you get a negative potential as well, isn't it?
Yeah. So it's a negative potential energy also.
Yes. That's
Oh.
why I say what you see, what you get for scalar calculation. Okay, if you see positive, you will get positive. If you see negative, you will get negative. Okay, clear?
Yeah, thank you, sir.
Okay, wow, I think we are overrun quite a lot here. Okay, that's why we need an extra class. Okay, I'll get back to the lecture notes. Okay, I'm staying out of it for too long. Okay, let me unshare first to get back to the what they call the lecture. Okay, I share the screen again. Okay, this is where we stop. Okay, without further delay, let's continue from here. Okay, we already discussed about the electric potential. I think you are quite clear just now, isn't it? Okay, all this you are sorry, too fast. Okay, start from here. I think you asked quite a lot of questions on that. I assume you already get the concept. Okay, so therefore, okay, from there I will go straight to this next item before we end the lesson. Okay, right. So you need to compare about the uniform field and also the radial field. Okay, so it's very simple. When we talk about uniform field, okay, you need to have the parallel plate to set up the uniform field. Okay, and to set up the uniform field is very straightforward and very easy. You just need to control the voltage and you know what is the gap. Okay, you should be able to create this uniform field. Okay, and why we call it uniform field is because no matter at which location within the parallel plate, the value of the electric field will be the same. Okay, right? No matter at which location, as long as within the parallel plate, the value of the electric field will be the same. Okay, so therefore, if you plot the graph of electric potential versus distance, you will get a straight line. Okay, and if you look at the gradient of the graph carefully, okay, the gradient of the graph is voltage over distance. Do you see that? And what is voltage over distance? Is your electric field, isn't it? We learned it in the previous lesson. Okay, so therefore uniform field, you're going to get a straight line graph. Okay, what if you have a radial field? Okay, radial field is come from a charge or point charge. So therefore the field is towards all direction. Okay, and all the while I emphasize that, okay, from the electrostatic force to electric field, I hope you still remember. Okay, so for the force, we know that the force is inversely proportional to the distance square. And from the electric field, we know that it is also inversely proportional to the distance square. This is so-called the inverse square law, right? So as a result, if you have a point charge, okay, the field will never uniform. Okay, the field will never uniform. Okay, if you travel from the center of the charge outwards, okay, the value of the what I call the electric field or the influence of the electrostatic force will getting weaker and weaker. It's because these two quantity inversely proportional to the distance square. Okay, so therefore, okay, if you further expand a little bit, okay, remember just now we have this formula, V equals to KQ over R. So from here, we know that the V is inversely proportional to the distance as well. Okay, so therefore, if you plot the graph of electric potential versus distance, you are not getting a straight line, but you get a curve. Do you see that? Okay, the reason is because the value of the electric field is not constant. Okay, it's unlike uniform field. Okay, right? I know some of you may ask why this is having a negative gradient. Okay, again, it involves the energy. All right. Okay, why we get the negative sign here? All right, the negative sign here is because the work done against the electric field. We try to bring this charge towards the positive plate. Okay, right? Positive charge to positive plate. Okay, so we are against the electric field. Okay, so therefore you get a negative gradient here. Okay, you get a negative gradient here. This is different from what we have seen just now about the positive energy and negative energy. This is different. This is purely we are looking at the electric field. Okay, right? So the gradient here, okay, is having a negative sign. Okay, because we are against the field. Right? Okay. Okay, let's carry on from here. Okay, last item. Okay, last item, then we can close shop for this lesson and we can proceed to the tutorial question. Okay, so the last item I'm going to emphasize to you is this equipotential line. Okay, this is very important. Okay, especially for those who plan to what they call the E&E in the future. Okay, so equipotential lines, what is that? Okay, so this is actually the line or locus of point where you're going to have the same electric potential. Okay, where you're going to have the same electric potential. Okay, let's start with the uniform field. Okay, so let's start with the uniform field. Let's look at it carefully, right? We need to use a voltage to connect to the parallel plate to set up the uniform electric field, isn't it? Okay, and still remember in the lesson there I did explain to you, okay, you need to connect the positive plate to the positive terminal of the battery and the negative terminal to the negative plate, isn't it? Right? So let's say you're using, let's say 10 volt here to set up this uniform electric field. So therefore, at the positive plate here, it will hold the voltage of 10 volt. Okay, and how about the negative plate here? It will hold the voltage of 0 volt. Okay, right? So therefore, okay, if you try to move from the positive plate towards the negative plate, the electric potential actually reducing. The electric potential actually reducing. Okay, it will reduce. Okay, let's say like what I show you in this figure 1.15 here. Okay, I divide the space between the parallel plate to 4 segments. Do you see that? Okay, this is the segment number 1, this is the segment number 2, number 3, and number 4. Do you see that? Okay, I divide the space between the parallel plate to 4 segments. Okay, so it means that you are having the 4 portion here. Okay, therefore, if you try to move, okay, from left towards right, okay, you will experience the reduce in the potential. Okay, you will experience the reduce in the potential. Okay, so at positive plate itself is 10 volt, but when you move to V1, okay, it will reduce to 7.5 volt. Okay, if you move to V2, it will reduce to 5 volt. Okay, to V3, it will reduce to 2.5 volt, and of course, when you reach the negative plate, you get 0 volt. Okay, so therefore, look at that. Look at all the dotted line that I draw for V1. Okay, so therefore, this dotted line will be the equipotential line. Okay, this will be the equipotential line. Means that no matter at which location you stand along this dotted line, you will get 7.5 volt. Do you see that? No matter where you stand, as long as along the dotted line here, you get 7.5 volt. So same thing if you proceed to the other one, right? Let's say at V3, 2.5 volt. Okay, no matter where you measure, okay, along this dotted line of 2.5 volt, okay, you will get 2.5 volt only. You won't get other value, right? You won't get other value. So therefore, the dotted line here is considered as the equipotential line for V3. Okay, so this is for uniform field. And how about the radial field? Okay, radial field will be a lot easier, okay, because you have a point charge, right? You have a point charge, and furthermore, you have this equation as well. Remember, just now we learned V equals to 1 over 4 pi epsilon naught Q over R. You see that? Okay, so as long as you fix a circumference, let's say the most inner dotted line here, okay, let me get a pointer first. Okay, let's say, look at my pointer here, okay? Right, look at this dotted line. As long as you stand or you walk along this dotted line, okay, it will maintain the same radius. It will maintain the same radius from the center of the charge, isn't it? Right, if I walk along this dotted line, look at my pointer, yeah? Okay, so you're having the same distance from the center of the charge, isn't it? So therefore, as long as you walk along this dotted line that I'm pointing now, okay, you're having the same potential because the value of the R is the same. Okay, so therefore this dotted line that I'm pointing now, okay, it will be the equipotential line for V1. Okay, if you increase the radius, let's say now, okay, the second dotted line from the center, if you walk along here, you will have the same voltage of V2 or same potential of V2, okay, because this is the equipotential line for V2 and so on. Okay, understand what is going on? Okay, let's proceed. to the next one. Okay, so this is what I described to you just now. Okay, for a radial field, okay, the charge will be the center of the series of concentric circles. Okay, right? So as long as you're walking on the same circumference, you should have the same electric potential and same electric field strength. Okay, and this dotted line is called equipotential line. All right. Okay, furthermore, the direction of the field is always at right angle to the equipotential line. You can go back to the previous diagram. Look at that. Okay, the red arrow here is the field lines. And look at the equipotential line. They are always perpendicular to the direction of the field. Okay, so same thing here for uniform field. You should be able to see all the dotted line here actually perpendicular to the field lines. Okay. All right. Okay, lines nearer to the charge will have the higher potential. Okay, this is because of the formula, isn't it? The V is inversely proportional to the distance. Okay, so closer to the charge, you have higher potential. Right, further from the charge, you have lower potential. Okay, and moving a charge along an equipotential line do not require any work. Right, it do not require any work. So it means that as long as the charge, let's say you have a test charge, the test charge, you want to move it along this circumference, actually you don't need to do any work. You see that? Okay, because no matter at which location along this dotted line, okay, the potential will be the same. Okay, so therefore, if the charge moving along this dotted line, right, no work need to be done. Okay. All right. Okay, so this is just a further explanation because from what I explained just to you just now, you may not able to get the idea. So therefore, I try to break it into several parts and use calculation to show you. Okay, right? So let's look at this situation. This is the same parapet that I showed you just now. We are using the 10 volt. Okay, right? And the total gap between this parapet, let's say, is 8 centimeter. Okay, and I divide it to 4 portions. Okay, so I will have 2 centimeter for each portion. Do you see that? So for the first dotted line, it will be V1, second dotted line, it will be V2, third dotted line will be V3, right? And of course, the distance will be different. Do you see that? When you refer, it's always refer to the ground. Okay, when we calculate the what I call the potential here, is always refer to the ground. Okay, so therefore, look at my distance here. I will put D1. Okay, if V1, right? V1 is at this location to this location, so it will be D1 here. So if you do the math, it will be 6 centimeter, and D2, okay, is referred to V2. Okay, if you do the math, it will be 4 centimeter, and the last one, V3 to the negative plate, it will be 2 centimeter as well. Okay, right? I just try to show you the simple math to show that, okay, how to get the equipotential line. Okay, first of all, you need to determine what is the field generated by this 10 volt and also this gap of 8 centimeter. So we can substitute all this value into the electric field equation. We get 125 Newton per coulomb. Okay, right? Since the electric field is uniform within the paraplates, okay, we already know that. Okay, so therefore, okay, you can use this equation, right, to determine what is the value of V1. So you can work backward from this equation. V1 equals to E D1. Okay, then we sub the E into here and look at D1. D1, okay, because V1 is here, so the distance to the ground or to the negative plate is 6 centimeter. So we get 7.5 volt. Okay, so therefore, along this dotted line, it will be 7.5 volt. Okay, and you can apply the same situation for the next two value of V, right, which is V2 and V3. Okay, you will find the value of the voltage as well, or the value of the potential. Okay, so V2 from the calculation, you get 5 volt. So means that, okay, along this dotted line, you get 5 volt. And along that dotted line, for V3, you get 2.5 volt. Okay, So this is just a simple calculation to show you how to get the value, okay, of the potential at a specific equipotential line. Okay, right. So we always take the negative plate as the ground. Okay, so ground is always having 0 volt. All right, so this is just to some 3D picture to give you a better view on this equipotential line. Okay, if you look at the side view or front view, okay, this dotted line we call equipotential line. But when you come to the 3D situation, okay, you are not looking at the line, you're actually looking at the plane. Okay, so therefore, if you look at this diagram, okay, this plane actually is the equipotential plane. Do you see that? Okay, so I try to highlight this to you is because later on when you go to UG, right, you are deal with the 3D stuff. Okay, you are not just determine the equipotential line. You eventually need to look at one specific surface. So therefore, as long as within how to say, as long as within this plane, okay, the potential should be the same because this is the equipotential plane. Okay. All right. Okay. So before we go to the tutorial, okay. So one of the application of this electric potential actually is the VR headset. Okay, virtual reality headset. Okay, some of you may have seen it before. So no matter it's for gaming, okay, or for aviation, or maybe in the war zone, right? You need to have this VR headset. And how it works, the principle is very straightforward. Okay, so basically it's because through many research together with the biology specialists and also the physicist plus the E&E engineer, okay, actually we have a very, very good model, right? We have a very good model or very good data, okay, on the motions at particular part in our body organ, okay, right? For instance, okay, the scientists, they know very well, okay, if you look at the iris of the eye, okay, there will be a positive charge of certain value, and at the retina there will be a certain charge of negative value. Okay, so in order to like control the this VR headset, okay, so the electrode within this VR headset, he need to sense the potential, okay, of the movement within the eyes. Okay, when our eyes can move, actually it's not like how to say the eyeball is moving. It's like, okay, if you want to look at the left hand side, actually you can control the movement of the iris. You see that? Okay, so like what I say, from the research data, they already know very well what is the charge at the iris and what is the charge at the retina. Okay, so therefore when you are wearing this virtual reality headset, okay, the electrode, there are many electrodes because you need the headset need to detect so many movement. You see, I just taking one of it. Okay, I'm just talking about one of it here. Okay, one of the electrode, okay, actually will be responsible for iris and also retina. Okay, so the one at the retina is a static charge, means this charge is not moving because your retina can't move, isn't it? But your iris can move left and right. Do you see that? Your iris can move left and right. So therefore, when you move the iris, this positive charge actually will travel to the left and travel to the right. Do you see that? Okay, now look at this carefully. Okay, the electrode actually will become the target. Do you see that? Okay, the electrode actually will become the target. Okay, we will try to determine what is the potential at the location of the electrode. Okay, we will determine the potential here. So therefore, okay, before the iris start to move, like in this case, I will taking the iris actually move to the left. Okay, so before the iris move to the left, actually we can calculate the potential. Okay, right? So we can calculate the potential. Okay, so the headset itself will record, okay, this is the value of the potential, because look at that, there will be a distance of R1 from the iris to the electrode. There will be a distance of R2 from the retina to the electrode. Do you see that? So still remember, if we have two charges, you are going to have two potential, isn't it? Right? So what you need to do is that okay, you just calculate the direct addition of these two potential. You will know what is the potential will be detected by this electrode. Understand the idea or not? Okay, so what if the iris is moving to the left, right? Like what I show here, the iris is moving to the left. You try to look at the left side, right? So this positive charge actually will move to the left. Okay, so the idea is that the electrode actually can sense the movement of the iris by means of he knows that the potential actually will change, isn't it? Do you agree? The potential will change. Just now when the iris at the center, okay, you will get a total potential based on the distance of R1 and R2, isn't it? Okay, but when the iris try to look at the left, right, means that this fella will move to the left, then the distance R1 will be reduced. Am I right? Agree or not? The distance R1 will be reduced. If the distance R1 reduced, means that the potential actually increase. Am I right? Okay, then electrode will detect the changes of the electric potential. Okay, right? So therefore, the electric potential due to the positive charge will increase. Okay, while the electric potential due to the negative charge remains constant. Okay, and of course, this electrode will be connected to the computer, right? So from the analysis of the computer will say, okay, this fella actually is looking to the left. So therefore, they will adjust whatever image that you're going to see. You understand the idea or not? Right? So basically, this is a very interesting science. Okay, it's a very interesting science. Okay, right? So actually, by the motion of the charge, it will change the potential detected by the electrode. Okay, and therefore, the computer will give feedback. All right, this fella is looking to the left, so you shall do something at the left. You see, right? Or this fella is looking to the right. Okay, when he looks to the right, the potential will reduce. Then the computer will tell, okay, try to do something at the left. Okay, this is just one of the electrodes. There are many electrodes within this VR headset. Some actually take care of looking up, looking down, looking far, looking near, right? Okay, so
sure, I have a question.
Yes.
Why will the potential difference increase due to the positive charge when it's looking towards the left?
Okay, when it looks to the left, what happened to the distance? The distance increase or decrease?
Oh, the distance decreases. Okay.
Yes. Okay.
Thank you.
Right. Okay. In the exam, of course, I wouldn't ask you about how this virtual reality headset work. Okay. Even if you will have a question on this VR headset, basically it will just ask you to calculate the potential difference. Okay. Let's say this fella moves to the left for how many right? You have to calculate the potential and so on, right? So it won't be like ask you to tell the grandmother story how this VR headset working and so on. Okay, don't worry, it's purely direct calculation. Okay, let's proceed. Oh, it's already going to 6. Okay, so like what we said, if the iris move to the left, the potential will increase. Okay. All right, example 1.5. I don't think we have time for tutorial. Okay. All right, example 1.5. Okay, this is very straightforward. We have a fixed point charge. Okay, you have only one charge here. Okay, at this point B. Okay, and point A and point C having the distance of, okay, A is 1 meter from B and C is 2 meter from B. Okay, you're asked to find the electric potential at C and also electric potential at A. Okay, this is a very simple question, isn't it? All right, so we already know that potential depends on two items. It depends on the charge of the source and it depends on the distance to the target, isn't it? When we say potential at C, C will be the target. When we say potential at A will be the target. All right, so therefore the calculation will be very straightforward. Okay, look at that, VC. Okay, so VC, we will take this distance. Okay, 2 meter, we get 9,000. And VB, we will take this distance, we get 18,000 volt. All right, how about potential difference VC minus VA? Okay, that will be very simple, isn't it? What you need to do is you just use VC minus VA. All right. So therefore you get negative 9,000 volt. Okay, right. How about part D here? Okay, part D, this is interesting. calculate the work done in bringing a charge, okay, Q2 to C. So this Q2 definitely will be the test charge, right? This will be the test charge. So you need to find the work done to bring this test charge to C, okay? So what shall we do here is that, okay, so remember, start from the definition of electric potential, okay? W equals to Q2 VC, okay? So remember, the charge in front here is the charge of the test charge. Okay, you get 9 millijoule. Okay, this is 9 millijoule. All right. Okay, so any question? Any question? Any question? Any question?
Still processing, sir.
Sorry again?
Still processing.
Still processing. Okay. All right, good.
Sir,
Okay.
can you please go to the previous slide?
Which one? This one?
The calculation.
Which one?
Yeah, this one. Thank you.
What happened?
We are calculating the potential at C just based on the charge B. So
you have only one charge here. Do you see that?
Right. Yeah. Thank
you have only one charge, but you have two target points, right? First question is target at C. The second question is target at A. Okay.
Yes, sir.
All right. Any other question? Okay, I don't think we have time for the tutorial. Okay, let's get back to our business on this extra class. I want you to decide now. Okay, what do you think? I already put the survey form there, but only 70 students response. Okay, and I tell you frankly, okay, everyone listen up. I tell you frankly, before online class, actually, this module is having 3 hours per week. Okay, 3 hours per week, and due to the online classes, we have to adjust the time for the classes because we have different students from a different country. We have to take care of the time zone issue, so we have no choice to squeeze all the classes to the afternoon session Malaysia time. Okay, and in order to put everything working properly, okay, so this module instead of 3 hours has been reduced to 2.5 hours. So we are short of 30 minutes. Okay, we are short of 30 minutes. So the university never say that we have to do the extra class, but I myself personally, I feel that missing of 30 minutes per week actually is a very, very big issue. Okay, so therefore I propose to have the extra class on this coming Saturday. Okay, right? So for 1.5 hours to about 2 hours, right? I don't want to fix it. Okay, if we can finish on time, it will be 1.5. If we can't, it will maximum it will be 2 hours. Okay, so that's the reason I propose the extra class. Okay, otherwise, you can feel that, right? I'm rushing. You see, right? You can, but I try not to, because all this involve a very critical or very important concept. I try not to rush. You see, okay. So therefore, I propose to have the this definitely is not the only extra class, because in the future I can predict we may have another 1 or 2. Okay, so what do you think? Okay, what do you think? So I still leave the survey open. All right, even though I say I'm going to close it Monday, but I will still leave it open. Can you please respond, right, to me? Let me know that whether you're okay for this coming Saturday or not, right? I already say, even though at night I can do it as well. Okay, so this is considered extra job for me. Okay, the university actually never asked me to do so, just that I want to do it. All right. So as like what I said, this coming Saturday extra class, if we are going to have it, it wouldn't be the only one, right? Because 1 week we are short of 30 minutes is actually a very, very big issue. I can complete everything on time, but there will be no time to do revision with you all, right? So due to that, I'm willing to give extra, right, which is not asked by the university. Okay, so please respond to the survey so that, like what I said, the rules, I say if 70% of the students agree to have it on this Saturday, then the class will be on. How about those, 30% of students can't make it? Don't worry, right? The video will be there. Okay, and in the future, if really critical, right, I might set the extra for this 30% student as well. Okay, right, I don't mind to do that, but I hope you to understand and cooperate to let me know as soon as possible so that I can do whatever arrangement for this extra class. Okay, so I don't think we can make it for the tutorial today. Okay, no choice, we have to push it on Thursday. Okay, all right, before we end, any question? Okay, actually you can leave now if you don't have any question, just like usual. If you don't have any question, you can leave now. Okay, you don't need to say, okay, you can go, right? Okay, it's already 6 o'clock in Malaysia time. If you feel that you want to leave, you can leave now. And if you have any question to ask, you can stay back. Okay, right? So please respond to this survey form so that I can make the arrangement. Okay, okay, any question? Any question?
No questions, sir, for me.
Okay, no question, you can leave now. Those who have question can stay back.
Okay, thank you very much, sir. Bye-bye.
Okay.
Okay, thank you so much,
Thank you,
sir.
sir.
Thank you, sir.
Thanks, sir. Thanks, sir.
Thank you, sir.
Yes.
Thank you, sir. Bye.
Bye bye.
Thank you, sir.
Tata. Okay.
What's your name?
Yes. Who's that?
Minna. I have a question, sir.
Yes. Regarding to?
Regarding the last example, could you please present the screen again?
Last example is the is about the point A and point C, right?
Yes.
Okay. One moment now. Let me share the screen. One moment, yeah.
Okay.
Okay. This is the one, right? Is this the one?
I still can't see the screen.
Okay, how about now? Can you see it?
Not yet.
Can you see the screen now?
Unfortunately, no.
I already shared the screen. Can you see it?
It's okay then. I can see it, but then it's okay, no problem. My question is, when we have, for example, point A and point C, they have no charge. Is that correct?
Yeah, there's no charges at point A.
Okay, so
so therefore, there's only one charge who set up the.
Okay, so what happens? Like we previously discussed.
Sorry again. I can't hear you.
Okay, so what happens? So for example, when we say potential at point C, so what happens to point B? Does it what happens exactly? So point B goes to the position of point C, or
no. The charge at point B is not moving, right? He just stay there. Right? Okay. So what we try to say here, potential at A and potential is okay. Can you still can you see my screen?
Yeah, now I can see the screen.
I see. Okay. This example, okay, this is electric field, but if I model it as our Earth, all right, okay, so let's say this is point B, okay, and this is point, no, okay, wait. One moment, yeah. Okay, imagine, all right, so this is our Earth, okay, all right, this is our Earth. The center of the Earth is point B, okay, and this is location A, and this is location C, okay. Location A is a mountain, okay, location C is a, let's say is a flat valley or whatever. Okay, so if you drop an object from the height of this mountain, there will be MGH, isn't it? Agree or not?
Yes,
And
agree.
if at location C, if you just, let's say this is not so high, okay, let's say this mountain is H1 and location C, the height is H2. Okay, if you drop the object from location C to the ground, before it drops, it will have the potential of MgH2. Agree?
Yes.
Right. So compare to this situation. Right. Compare to this situation. All right. So basically, B is our Earth. Okay, B is our Earth, and point A. Okay, let's say it will be this location, A. All right. Okay, and point C, it will be this location. Okay, so because our Earth here generate the gravitational field, right? So therefore, at different location, different height, it will be different potential. So this situation is that B is the planet Earth. Okay, the charge Q1, right, at the location B. This is the planet Earth. Okay, A and C basically different location at different height. You see that? Understand the idea or not?
Yes, understood.
Sure. Huh?
Yes.
Okay, any other question on that?
Okay, so like can A and C be charges, or it's always gonna be a point?
If A and C be a charges, then the question will be different already, right? Like what I said, whenever you have multiple charges in the question, okay, you must identify who set a field and where will be the target. Okay, let's say we modify this question a little bit. Let's say we have a charge here, another charge here. Okay, let's say this is Q2. Okay, you're having a 4 microcoulomb, let's say. Okay, so if the question asks for electric potential at C, what shall we do? Like what I mentioned, first you have to identify how many target, right? And how many charges set the field. Okay, you have only one target, which is C, right? And then you have 2 charges set the field. Am I right? Okay.
Yes.
So therefore, the potential at C, okay, is contributed by 2 charges. So therefore, it's VA plus VB. You see that? Okay, and just do the substitution. VA is 4 microcoulomb. Okay, and the distance from A to C is 3 meters. Am I right? Am I right? And the distance, okay, now go to VB.